Hello friends, I am Boyobde and you are watching Unplanned Pulse. Today we are looking at matrix chain multiplication. Let's start with a simple question. A1 which row number is 3 and column number is 5 and A2 a matrix, A3 a matrix. We all know mathematically matrix multiplication is associative, meaning if we have 3 matrices, let A1, A2 and A3, the final result is the same regardless of how we group them. From following question, there can be two cases. Case 1, at first do multiplication between A1 and A2, then multiply with A3. And in case 2, at first do multiplication between A2 and A3 and then multiply with A1. As multiplication is associative for matrix, so for both the cases answer will be same, but something which will differ is computation. Now if we calculate for case 1, the first multiplication will take 30 computation and the last one will take 24 computations. So total computations will take 30 plus 24, 54. Now let's see for case 2. Here the first multiplication will take 40 computations and the last multiplication will take 60 computations. So total computation for case 2 is 40 plus 60, 100. So we can say case 1 is taking minimum time, almost half of the case 2. But when we have a long chain of matrices, finding the cheapest order is critical. That's the problem we are solving today. Now there is a formula by which we can calculate the number of combinations you can have by n number of matrices. N is here number of matrices and Pn is number of parenthesization. If n equals to 1, there will be one combination, and if n is greater than equals to 2, then there will be Pn equals to summation of k equals to 1 to n minus 1 p of k into p of n minus k. Now if n equals to 2, p2 will be 1 from calculation, because when n equals to 1, p of 1 is 1, so the answer is simply 1. And when n equals to 3, p3 will be 2. From the previous question we get for n equals to 2, pn is 1. So here if we put 1 at the place of p2, we will get p3 equals to 2. So this is how you can calculate the combinations by number of matrices. Now let me introduce you with the dimension array P, which represents the sizes of matrices. With an example, suppose it is said to perform multiplication among A1, A2, A3 and A4. The P array will look like this. Now let's break chain into smaller subproblems, solve them and store the results into smaller subproblems. Next we need two tables. One is M table and one is S table. The M table will store minimum multiplication cost for any subchain, and the S table will act like our map. It stores the specific point called K between I and J. Now let's see how we can actually fill the M and S table. Keep one thing in mind, the M table, I and J both will go to 1 to n. But for S table, I will go to 1 to n minus 1 and J will go to 2 to n. Now to find the M table values, there is a formula. If I equals to then J, then M of Ij equals to 0. So we can simply put 0 at the M table where I equals to J is happening. Now let's start calculating and fill the M and S table. Let's start with M of 1, 2, this one. So this case K can be 1 only. After calculation, store the value in M table and S table. Now do the same for others. For M of 2, 3, the K will be 2. Now why it is 2? Because the K value can be greater than or equal to the I, but it must be less than J. Again put the value in M table and put the K value in S table. Done. For M of 3, 4, this part k will be 3. You can see the calculation. And now let's update the m table and s table. Next one is m of 1 3. For this k can be 1 and 2. For this, now we have to find the minimum value of m of 1 3 for values of k, and that value will be stored in m table, and for which k value we get our minimum m of 1 3 will be stored in s table. Now let's see calculations. For k equals to 1, m of 1 3 will be 1750, and for k equals to 2, m of 1 3 will be 4500. So minimum value is 1750 and the k value is 1. So store it in the tables. Same way you can find for m of 2 4 as well as m of 1 4. For these two I am not going to show the calculations. Do them with your own. The final m table and s table will look like this. Now we can find our final expression using a function, or you can say a algorithm, which is known as print optimal parents. It just reads the s table and builds the final expression. The algorithm says if I equals to j, it means we have isolated a single matrix. Print the matrix and stop. Now for the else part, where I and j are different, this is where we consult our s table. Now let's understand the whole algorithm process using a table. One more thing I want you to know is after printing the opening parenthesis, it executes the next line, print optimal parents s of ij, but the next two lines are put on pause, this one and this one, because a computer uses recursion stack to remember what it was doing. It pushes this pending instruction into the stack so it does not forget to execute them later. Let's start from the top. S of 1 4, I not equals to 0, so go to the else part. First print opening bracket into the expression, then print optimal parents function will call. As at a time one function call is possible, so the next function will go to the stack. Now if you see, the function is actually calling is pop s of 1 3. Now when I equals to 1 and j equals to 3, it will again go to the else part and print another opening bracket, and the next function is stored into the stack, and the function is actually calling, this function is actually calling pop s of 1 comma 1. Now I equals to 1 and j equals to 1, so if part is 2 and it will print a1. Now it unfinished function calls will occur and stack pop will happen. Pop s of 1 3 plus 1 comma 3 will pop from the stack, and a closing parenthesis will push into the stack. This one will pop and this will pushed. Now this function is actually calling what? This is calling pop s comma 2 comma 3. As I is not equals to j again, it will again go to the else part and print a opening parenthesis. Now it will call pop s comma 2 comma s of 2 3, and the next function will move to the stack. Now the function is actually calling pop s of 2 comma 2, as I equals to 2 and j equals to 2, so it will go to the if part and print a2. Now it will again go to the stack and pop the function, this one, and call it and push it again, push a closing bracket at the place of it. and the function is calling pop s comma 3 actually. Again I equals to 3 and j equals to 3, so it will go to the if part and print a3. Now it will again start propping from the stack. As closing bracket is encountered, pop it and print it into the expression. See, here you can see the closing bracket as a character in stack, but in reality it actually stores as a print closing bracket type instruction. Okay, like it is stored as an instruction which says that whenever the instruction calls, you have to print the closing bracket. Now pop the first one and add to the expression. After that, as well as pop the next and add it to the expression. Now pop the function and call it and push a closing bracket at the place of it. Now this function is actually calling nothing but pop s comma 4 comma 4. As I equals to 4 and j equals to 4, so it will go to the if part again and print a4. Now it will again pop from the stack. As closing bracket is encountered, pop it and print it into the expression. As now the stack is empty, our work is done, and the final output is this one, right? So this is how you can find the most efficient way to multiply a chain of matrices using the print optimal parenthesization. That's all for today. Thank you for watching. If you found this video helpful, don't forget to hit the like button, subscribe the channel and share it with your friends. See you in the next video.